So, hello and welcome to the fourth edition of these online lectures. And so, in the lecture today, we are going to understand how electric and magnetic fields transform into each other under Lorentz transformations. And we shall today do this precisely. We have seen earlier that this happens. So, what is an electric field in one frame of reference becomes a magnetic field if you're looking at it from another frame of reference. Now, at the beginning, this particular thing thing looks a little, it looks that it might be a little problematic, because remember, so far the objects that we have seen that have nice properties under Lorentz transformations are four vectors. But now we have three vectors, the electric field and the magnetic field. So the first idea that you might have is that you would like to transform these three vectors into four vectors. Now, if you do, if you somehow invent something such that you make the electric electric three vector into a four vector, a transformation of this will just mix components of the electric vector, and it will not involve a magnetic field out there. So clearly we have to do something more, okay? And in order to understand this, we will revisit something that you have already done before, but then we are going to give it a new twist, okay? So we start off today by saying that this gate there's re-emphasizing the importance of gauge invariance in electromagnetism. Okay. So you have seen before that when you were looking at electrostatics, you had del cross E equal to 0, which meant that E could be written as the gradient of some scalar function phi. And in magnetostatics, you had del cross B equal to 0 and del dot B equal to 0. I'm sorry. That meant that B could be expressed as a curl of some vector A. So we call phi and A are scalar and vector potentials, right? So now we have Maxwell's equations. Sorry, Maxwell's equations. So as you all are familiar with, del dot E is rho over epsilon naught, del dot B is 0, del cross E is minus del B del T, and del cross B is mu naught J plus mu naught epsilon naught del E del T. Now you see del dot B is still equal to 0. So since del dot B is equal to 0, we can write B as the curl of vector potential. This still holds. But del cross E is no longer equal to 0, right? So that has to be changed. And the change is, this is pretty straightforward. So let's do this. So del cross E is minus del T of, now you have this as a curl of A, right? So what is happening is, instead of curl of E being 0, what you have is curl of E plus del A del T being equal to 0. So we will call this particular object. So this is going to be curl of E. So let's rephrase this. So what do we have? We have E plus del A del T being equal to minus gradient of some phi. Okay. So the changed expressions are E is minus grad of phi minus del A del T, and B still remains curl of A. Okay. So phi, of course, is now phi of x and t, and A is A of x and t. Now, you need to also remember that, as before, so there is also no unique choice of phi and A. We can always shift A to A plus some gradient of some scalar x or chi. So this leaves B invariant. But now what we need to do is we need to also shift phi to keep E invariant. And what do we need to do? So phi has to go to phi minus del chi del t when A goes to A plus gradient of chi to keep electric field invariant. Okay, so these are gauge transformations. And these are extremely important. Okay, so let me sort of underline them in red for you. These are very, very important things. But as you can understand, there is this subtle way that you can already see that phi and A seem to be mixed, and we have a scalar and we have a 3 vector, and thus it's sort of ripe to make this into a 4 vector. Okay, so now you can define a 4 vector. So now define a 4 vector. So let's just get back to blue. define a 4 vector A, let's call this upper mu, and we will have this phi over C and A vector. We will see why we had to put in a factor of C. This is something that will become apparent. If this is the upper one, then you also know that the lower component is going to be phi over C and minus A vector. So that's something that you also know. So that is equivalently A mu. So the gauge transformations take this very nice form of A mu going to A mu minus del mu of chi. Remember, del mu was just given by 1 over C, this was according to my conventions, 1 over C del t and gradient. So this is what happens. So this is going to be, so this is in a very nice form. So this is what we have, okay? So you see, now you can see where this factor of 1 over C comes in. As you see, if you're looking at phi over C, so if you're looking at A naught, let's just rewrite this. So A naught goes to A naught minus del naught chi. So this essentially means A naught is, as you can see, phi over C. This goes to phi over C minus del naught is 1 over C del chi del t. So, this takes care of factors of C, and you get phi goes to phi minus del chi del t. Essentially what you had upstairs. So this is a nice sort of covariant form of this this equation. So this is, okay, let me put a box in here. Right, so this is a nice form, okay? And you need to remember that this object is, okay, no. So, yeah, so this is the object that we are actually interested in. So this A mu has been now made into a 4 vector. Very good. So the next thing to do now, so now that we have a 4 vector, we want to try and figure out how this fits into the electromagnetic theory, right? And for that, what we are going to do is we are going to think about the symmetries of the problem first. So let's think about this for a minute, okay? So we have electric field. So this is Ex, Ey, Ez, and we have the magnetic field, which is Bx, By, Bz. And if you have these, so these are 6 independent components. Now you have a 4 vector A mu, and you have, it's very clear that A mu is, so the electric field and the magnetic field are related to this 4 vector A mu by some factors of del's, right? But before we get to that, let's try and see. So if you have 6 independent. So we need an object that transforms nicely under Lorentz transformations and has 6 independent components. Of course, a 4 vector will not do because we have 6 entries. So the next best thing that we can do is we can maybe think of some matrix F mu nu. So if we think of a matrix F mu nu, so this is what this is, mu and nu run from, so take value 0, 1, 2, 3. And so this particular object, any such object, will have 16 entries. Okay, so F mu nu, let's just write this down. So F00, F01, F02, F03, and we can go on, F10, F20, F30, F11, F12, F13, F21, F22, F23, F31, F32, F33. Now this is a matrix. Now what are the things that we can do? We can say that this is a symmetric matrix. Suppose this were a symmetric matrix. F mu nu is symmetric. So that means that F mu nu is equal to F nu mu. Okay, so what happens then is that all these, diagonal entries, so for example, F01 becomes equal to F10, etc. So if you look at this, if you look at the matrix here, so what happens is that these 6 objects get related to these 6 objects, right? So that's fine, but we are also left with the diagonal ones. So what happens is that there are 6 independent off diagonal objects plus 4 diagonal entries. So that makes it 10 independent objects. Entries. So this doesn't quite do. Okay. Now suppose you have, F mu nu is antisymmetric. So that means F mu nu is equal to minus F nu mu. So what happens if that's the case? Then again, the thing here, the off diagonal entries are again related. So off diagonal entries are again related. But now diagonal entries are equal to 0 because of what? F mu nu is equal to minus F nu mu, nu mu. So suppose you had Fii, this will be equal to minus Fii. So that would just mean Fii is equal to 0. So F11 is equal to 0, F22 equal to 0, and so on. So now, so F mu nu antisymmetric does the job. So it has 6 independent entries. Okay, so we want to build some second ranked object F mu nu such that it will transform nicely under these under these Lorentz transformations, and it'll also be antisymmetric in the indices mu and nu, so that there will be 6 independent components. Now, what is F mu nu? What can we form? So this is, to use a fancy language, to use some fancy language, do not get scared by this. So this is called the electromagnetic. Okay, so let's write this down. So the electromagnetic tensor. So you should not get spooked by this term. It's just a 4x4 matrix. So electromagnetic tensor is going to be defined as F mu nu, as we have seen, is going to be del mu a nu minus del nu a mu. So we are going to be defining as this. So you remember that del mu is defined as 1 over c del t and delta, and a mu is defined as phi over c and minus a vector. All right, so this is this. So let's try and see what this guy actually is. So let's look at F01. Okay, this is what? This is 1 over c into del t 1. So a mu has to be 1. Okay, let me try and write this thing down first. Okay, so this has to be del 0 a1 minus del 1 a0. Okay, what is del 0? Del 0 is 1 over c del t. A1 is minus ax, right? Minus del 1. Del 1 is just del x. And a0 is what? A0 is phi over c. So let's write this down. So this is minus 1 over c del ax del t minus 1 over c del phi del x. Now what is this? Remember what the electric field was. We just derived it just a few minutes back. and this electric field was given by minus grad phi minus, so the electric field was given by this expression here. Okay? So now what do we want to do? So let's just so this expression means that that what you have here is nothing but Ex over C. Okay? Similarly, you can do it for the other one. So F02 is going to be Ey over C. F03 is going to be Ez over C. Now the other interesting thing is going to be F12. So let's try and work this out as well. So this one is what? This one is del 1 A2 minus del 2 A1. Del 1 A2 minus del 2 A1 is, so del 1 is del x, A2 is minus a y vector minus del y of minus ax. So this is minus of del ay del x minus del ax del y. This is nothing but minus of Bz. Now you can do the rest, and what you're going to find, and okay, so another thing that I should just point out, this is of course true, but it's good to see this straight away. So if you're looking at F00 for example, this is this del 0 A0 minus del 0 A0. This is explicitly equal to 0. So what is F? F mu nu is the following. So 0, so this is Ex over C, Ey over C, Ez over C, minus Ex over C, minus Ey over C, minus Ez over C. 0, you need to be careful about the signs out here. I encourage you to go back and do this. Bz, By. So this is Bz, this is 0, this is minus Bx, this one is minus By, this is Bx, and this is 0. So this is what your electromagnetic tensor is. Remember that if you were to try and put both these indices up, you can again use your Minkowski metric to raise this. So F upstairs mu nu is eta mu rho eta nu sigma F rho sigma. And if you compute this, what you will find is that this is a very similar form, but it has some signs which are switched over. So this is minus Ex over C, minus Ey over C, minus Ez over C, it's Ex over C, Ey over C, Ez over C. This is 0. This does not change sign. All right, so this is what it's going to be. So this, you remember, is you just take the lower matrix multiplied by 2 of these etas, and you just get this matrix, right? So that's what you have to do. So, just to make things a little more clear, this is just 1 minus 1 minus 1 minus 1 1 minus 1 minus 1 minus 1 into the into this particular matrix 0 ax by c, ey by c, ez by c, and and then you just get this form. Okay, so that's what you have to do. And now remember that, so if you were to look at f mu nu, so this is nothing but del mu a nu minus del mu a mu. Now these objects, these are 4 vectors, these transform. So if you are looking at del mu a mu, these are 4 vectors. So a mu transforms as lambda times a. So what will happen is f is going to transform as lambda times lambda into f, because so del mu, so these are 4 vectors, these transform in this way. So f is also going to transform in this way. When written out in terms of indices, what is going to happen is f prime mu nu is going to be lambda mu rho lambda nu sigma f of rho sigma. Okay, so you can do all of this in terms of matrices, and this will be fine. All right, so these are so if you want to think of this a little bit more in so let me rephrase this a little bit actually. So let me just okay, let me just rephrase this a little bit. Okay, so let's try to get this in the proper matrix form. So so this is the proper so let me erase this and let me bring this here. So this one was right, what I said about so this is the form of the transformation, this. And in terms of matrix language, if you want to do it, then f primed is just lambda f lambda transpose. So this is going to be the way that f transforms. Okay, this is important, and let me also box this up. Okay. Okay, no. So not even that. Let me see if this one helps. Yeah, that's better. Very good. So we have now understood how these how the f is going to transform. Another quick thing that I want to show you is that, of course, we had this gauge invariance, right? So electric and magnetic fields did not transform, and I mean under this gauge transformations. So f is an object which harbors whose entries are electric fields and magnetic fields. So I mean clearly it should not transform under gauge transformations. Let's quickly see this. Okay. So f, so what did we have? We constructed this gauge transformation where a mu goes to a mu minus del mu chi. So this essentially means that f mu nu is going to go to something which is, so f mu nu is del mu a nu minus del nu a mu. So this is going to go to del mu of a mu minus, sorry, a nu minus del nu chi minus del nu of a mu minus del mu chi. So you see that this is equal to del mu a nu minus del nu a mu minus of del nu chi minus of del nu plus del mu chi. Now we know that partial derivatives commute, partial derivatives commute. So that essentially means that del nu acting on some object psi is equal to del mu acting on the same object psi. So this means that f mu nu is going to, under gauge transformations, will go to f mu nu plus del nu chi plus del mu chi, which is just f mu nu. So f mu nu is gauge invariant. Okay, so this is what we have done now. So what we will do is we will quickly, so I'm going to actually end this lecture here for now, and we will just take it on very shortly in the next lecture, that how we are going to transform these fields into each other, and we will see some explicit examples as well. So what I wanted to just re-examine in this particular short lecture today is that we have tried to build something out of. Let me just re-emphasize what we have done. Okay, so we started off by looking at gauge invariance as you had earlier seen it. So when you had looked at electrostatics and magnetostatics, you had seen that the electric field and the magnetic field, these objects could be looked at, these objects could be expressed in terms of scalar and vector potentials. Now, when you are going to look at Maxwell's equations, generalizing from what you had in electrostatics and magnetostatics, since the del dot B equal to 0 equation still stays, it means that you can still express B as a curl of some vector. But now, if you were to try to understand how to fit this scalar potential in, you had to do a little bit more work. And once you did it, you saw that you could express E and B in terms of the scalar and vector potential. E now had this extra piece which was del A del T. We then revisited the fact that there was no unique choice for phi and A. You can always move A by the gradient of a scalar function chi, and this leaves B invariant. But now, since A and phi are mixed up in the electric field, what we have to do is, in order to keep E invariant, we also have to do a compensating transformation on phi. And this was given by this equation here. Okay. Now the fact that phi and A were mixed up offered us a door into what we have to. Offered us a glimpse into what we had to really do. We had to group up phi and a and form a 4 vector. Okay, so a mu was defined as the boxed equation here. So a mu here. So a mu upstairs was defined as phi over c and a vector, and a mu downstairs was phi over c and minus a vector. Gauge transformations took a very nice form, which just meant that a mu went to a mu minus del mu of chi. And I showed you, how this fit into this earlier equation. And so that was the first thing that we did. Now I wanted to stress to you that you had these 6 objects, 6 independent objects, 3 components of the electric vector, 3 components of the magnetic vector, and we were in search of something that transforms nicely under Lorentz transformations and also has 6 independent components. Clearly, one 4 vector will not do, so we had to go to the next thing, an object which has 2 indices. Now, if an object had 2 indices, if you were to write it in form of a matrix, this matrix will have 16 entries, 4 into 4 for each 4 of these. So there will be 4 of 4 entries for mu and nu. So 4 into 4 will be 16 entries. Now, if we were to, so now what we need to do is we need to get from 16 entries down to 6 independent entries. So the first thing that we could assume is that f mu nu is symmetric. If we did that, then what would happen is that of course the off diagonal elements will get related. So those would be 6, but there will also be diagonal entries which would form 4 more independent guys. So there will be 10 independent entries. So that doesn't do the job. Now let's suppose the next thing where f mu nu is antisymmetric. If f mu nu is antisymmetric, then what is going to happen is that again the off diagonal elements will get related. But now since f mu nu is antisymmetric, the things in between the diagonal entries will also have to be 0. So now we get our desired 6 entries. So f mu nu with f mu nu being antisymmetric does the job. Now, what is f mu nu? How do we actually get to f mu nu? And of course, since we had defined a mu, the answer should obviously involve a mu. And the other thing that we saw earlier is that the electric and magnetic fields that we expressed were written in terms of some derivatives acting on a mu. So the natural choice would be to act del mu on some a nu to get f mu nu. We also have to make it antisymmetric, and hence this form of f mu nu is going to be our guess. Now let's see if we have made the right choice or not. We can look at f0I, and we saw that so that is going to be the electric vector. It's going to be EIs. For example, f01 we explicitly saw was EX over C. And similarly, if you wanted to look at Fij, that is going to be related to the magnetic field B. Fij, spatial indices. For example, F12 is going to be related to Bz. So if you just write down all of these guys, what is going to happen is that f mu nu is going to take the form that I've written down out here. If you want to transform these indices into upper indices, what you have to do is you have to multiply them by etas. So you multiply this object that I've just shown you by these 2 etas, and then what you get is going to be this f mu nu upstairs, which is written here. Okay. So let me erase these hideous red marks here for the moment. And now, del mu is going to transform nicely, a nu is going to transform nicely. So what is going to happen? F mu nu is obviously going to transform in a nice way. So F mu nu is going to transform in this way that I sort of circle. Written down in terms of matrices, it's F prime goes to lambda F lambda transpose. This is what we are going to be focusing on. I'll also try and see if I can clearly show you this. So this was how F is going to transform. And lastly, what we tried to impress on you is that since F is made up of electric and magnetic fields, this has to be gauge invariant, and we actually tried to do that. We looked at the gauge invariance and wrote it down explicitly here, and we impose the fact that partial derivatives commute to say that del mu nu of psi is del mu of psi, and that just meant that F mu nu is gauge invariant. Okay, you could have reversed your argument, saying starting off with this and saying that F mu nu is gauge invariant, and hence it has to be constructed out of electric fields and magnetic fields. But okay, so that's what we learned in this shorter lecture today. What I'm going to be doing in the next lecture is explicitly showing you, for example, what is going to happen under boosts and so on. That is going to come up in a few minutes time. So yes, so I will be seeing you then. Thanks.